Hello, so my name is Julien Sommer. I was asked to talk a bit about NEMO ocean modeling framework here to this audience. So I understand that it's quite a mixed audience with a lot of students and people not really all of them accustomed to the basics of to the discretization of partial differential equations and things like this. So I try and be as superficial as possible. And I shall also apologize. I'm only here for a couple of hours, so I will leave soon after this discussion. Don't hesitate to drop me emails or to contact me if there are any questions after this talk. So I'll be talking about NEMO, its present status and its future evolution. And to a large extent, this is not my work that I'm showing here. It's the contribution of a large number of people, and even the slides are not all mine here. Okay. So I guess the entry point is, you're probably not surprised about that, but if you go to Copernicus data portal, you see that there are two types of different products there. There are products based on observation only, or to a large extent observations, and products based on models. So there's from the very beginning here some sort of an intricacy between the observational products and the model products. So what are we talking about here? We're talking about a model. A model, it basically refers to the software, the piece of software code that you're using for implementing a physically consistent description of the three-dimensional state of the ocean and its evolution. Okay, so that's something that we need for Copernicus services. And why is that? The first point is that we don't have an observational network dense enough for covering the actual needs of the users. So we need somehow to interpolate, extrapolate the observational data in space and in time. The point is, the best way we have so far for performing this interpolation is through physically based understanding of the dynamics. You could fancy or imagine some data-driven approaches. So far, they are not there yet. So the best way we can extrapolate this information is through a good physical understanding and a good implementation of this physical understanding into a computer program. So there are also another aspect here, the fact that beyond what we observe, there are also things that we don't observe. And we know that those things can matter in terms of the evolution of the ocean over short timescales or long timescales. So we need to account for them. And the only way to do that is through your a priori knowledge of the underlying physics. And to be frank, even if there's such a distinction between, on the one hand, the model product and on the other hand, the observational product, it's probably fair to say that it's probably more sort of a continuum of products that we're having here. Even the reprocessing of altimeter data that are one key source of information used in the products we're talking about here, even those products, they actually use physical models for getting to the actual measurement itself. So it's not as if there was model on the one side and observations on the other. It's a continuum. Important to notice that over the last 20 years or so, there has been a very clear co-development or joint history between the emergence of operational oceanography and ocean modeling capabilities. And to a large extent, ocean models have driven or contributed to the evolution of the modern observing network. I mean, it goes in the two directions there, but basically at the same time we got this fantastic observation network we have now with Argo, altimetry, etc. We also built up the model that can ingest this information. And that's particularly true at the European level, where we had this fantastic coordination of institutions for building something that we're describing here. So that's a really nice story that happened over the last 20 years, I guess, and to a large extent, the actual development of ocean models in Europe is some sort of a consequence of Siemens, as far as I can tell. Well. I've been talking about ocean models here and about NEMO. I was vague a bit. I guess it's probably fair to say that a large fraction of the monitoring and forecasting centers in Siemens are actually using the same ocean model. So we're talking about NEMO, and for what I'll be talking about for the next 25 minutes or so, I'll mostly be focusing on this particular ocean model called NEMO. I will try and discuss the basics of Nemo as an ocean model, and also try and foresee what sort of evolution or trends in evolution could have an impact on the evolution of future products in CMEMS. Okay, so three moments in my talk. I talk about Nemo, the Nemo Ocean Engine as an organization. I then talk about the very basic concepts of physically based ocean modeling, and I'll then try and highlight a couple of key drivers for evolution of Nemo in the future. Okay, Nemo Ocean Engine. So what are we talking about? We're talking about, basically, from the very basic level, we're talking about several hundred thousands of lines of Fortran code, so that's boring. And that mostly reflects 15 years of work of a really large group of people. Okay, it's distributed as an open source code, and the very fact that it's distributed from the beginning as an open source code has also a lot to do with the actual open mindset that we have in this audience here. So that's key from my perspective. This tool, this software, combines a number of different building blocks, and those building blocks allow you to build a particular application depending on your need. Those building blocks are a description of what we call the blue ocean. So that's basically an implementation of our knowledge of the ocean dynamics that prescribes the evolution of the currents and the physical properties of the ocean, temperature, salinity. There's also the white ocean. It's the component that describes the evolution of sea ice. That is, from our perspective, clearly one component of the ocean as a component of the global climate system. So this white ocean describes the evolution of the thickness, of the concentration, of the drift of sea ice. There's also a component dedicated to the description of the green ocean. So the green ocean here is the marine biogeochemistry. There, obviously, we're getting to a world where we don't quite have exactly the same knowledge of the underlying physics, but still, to some extent, some of the key properties can be phrased in the same kind of framework, and in particular, the question of the transport of biogeochemical traces. Component number 4 is a functionality that allows the model for your application, you can have local increased resolution through a tool that we call Agrif. And there's also a number of building blocks and tools for performing data assimilation with Nemo. Okay, so Nemo, it's one single thing that has several components inside, and you pick up the one you need when you build up an application. Now, if you look at the actual range of application, I'd just like to let you understand that it's a large spectrum that we're having here within CMEMS, but also beyond. So if you start from CMEMS catalog, obviously a fraction of those operational forecasts here actually use Nemo to provide a physically consistent forecast of ocean dynamics over several days. It's also true, as we've been introduced to by Simona for ocean reanalysis, that they really need the physical consistency coming from our a priori knowledge of the underlying physics for extrapolating and interpolating the data over several decades so that we could describe consistently the evolution of the ocean over long time scales. And it goes actually further beyond what's in CMEMS products. To a large extent, one of the key drivers of Nemo is the application of, our need to describe the ocean when we perform decadal predictions of climate variability, or when we try and project the evolution of climate over centennial timescales. For that, we need an ocean component, and in Europe right now, 6 of the Earth system models used for CMIP 6 model intercomparison projects actually use Nemo as their ocean component. Okay, so this is just an illustration of how CMIP 6 project is organized. The baseline here, for those of you who are not familiar with that, is that those simulations actually feed the papers that go eventually within the IPCC report. So basically, Nemo is a key element of the European strategy for climate forecasting. There are also another wide range. There are probably that's only one slide here, but that's probably the majority of the applications here. There are a large number of scientific applications of NEMO, a wide variety of model configurations, model setups. They can be regional or global. They can be coupled to the atmosphere or only forced by the atmosphere. They can use that as simulation or not. They can use the biogeochemical component or not. But basically, there's something like 100 projects ongoing that use NEMO and focus on a number of questions of ocean relevance, starting from the understanding of the mechanisms that drive the seasonal to decadal variability in the ocean, how the scale interactions within the ocean can affect the larger scales. There are also a large number of applications for paleoclimate reconstructions. There are also applications in the context of field campaign for accompanying the deployment of dedicated field campaign for studying ocean processes. There are pilot studies with tides. There are, NEMO is used also for developing data assimilation techniques, or looking at the exchanges between the continental margin and the open ocean. Basically, that's a research tool. And that's the key point here. At the same time, we built a tool for operational oceanography. We also built a tool for research. And I think this is exactly the kind of complementarity that we should keep in the future. Okay, so how does this work? It works because there's a consortium there. There's a consortium of institutions, 6 of them, operational and research institutions that have decided to team up and pull out their resources for developing this ocean model over a long time scale. So basically those institutions here are there, so 6 of them. I will not go through all the list. I paid attention as a Simona to really put all the logos here, so there's no issue. Everyone is there. So basically those institutions, they team up something like 10 full-time equivalent people corresponding to 30 real-life people that work together within what we call the system team, NEMO system team, under the coordination of Claire Levy at CNRS and scientific leadership of Govan Madek at CNRS too. So this team is in charge of further developing the code and maintaining the code sustainably over long time scales. This activity is also coordinated or advised by what we call the NEMO Developers Committee. That's a group of experts that gather twice a year and review the actual code and make proposition or discuss what could be the future pieces of code that we put within this framework. And from my standpoint, most importantly, this all works because there's a community, there's a users community behind NEMO, a large, vibrant community of users, a large fraction of which is involved in what we call the DRACAR coordination, and there again, it's the European level that is the natural scale for this particular coordination. Okay, so this was just for the organizational aspects and where you could find bits and pieces of NEMO within this environment. For the next couple of minutes, I'll get into a more hardcore science, I guess. I try to be as concise as possible. So first, the basic concepts of physically based ocean modeling. Take a deep breath. Look at those equations. So I don't want to bother you with all this, but the baseline here is that at the very basic level, an ocean model implements what we know the best about how state variables of a continuous system can evolve over time. Basically what we call the conservation laws. So you conserve momentum, you conserve energy, you conserve heat, you conserve salt. This all transformed into a number of equations, okay? Those equations are called the primitive equations. There are a number of hypotheses for them to be valid. I will not review them here, but basically you should keep in mind that we're describing the evolution of horizontal current, U, V, temperature, salinity, and all the other variables, at least for what concerns the blue component, are derived from this. Okay, this is true for density, vertical velocity, and this is for the very basics, the core of what's in the model. Then you need boundary conditions. They come from the atmosphere, and you exchange a number of things with the atmosphere. You exchange momentum, you exchange heat and salt. Okay, so the baseline is this. Forget about the equation. Basically what we're looking at, it's that sort of a system, okay? So that's a partial differential equation, multi-dimensional partial differential equation. I just put one term out here. It's what we call the advective term due to the transport by the horizontal currents. But basically, y here is the state vector of the ocean. And the function here, the fy, includes a large number of terms, things you know, things you don't know, and what you're interested in is describing the evolution of y, given a particular knowledge of y at time t. You want to know how it will evolve over time. To do that, we use what we call the discretization. Okay, so that's a very standard kind of techniques for geoscientific modeling. We're defining a grid. A grid is first a spatial grid, so that's just a random example here, a structured grid. There are points there. You don't want to get into the detail. And there's that's in the horizontal plane, and that's in the vertical plane there. So what you see here is that we're cutting space, and we're cutting the ocean into boxes. Okay, those boxes, we will describe the evolution of the temperature, salinity, and currents within those boxes. Okay, this will evolve according to laws that we can prescribe from our knowledge of the governing equations. Okay, so this is basically what we're doing here. In practice, it comes with a spatial discretization. We're computing fluxes across the boundaries of the boxes based on those equations, and from that we can obtain an idea of how the system will evolve from time t to time t plus delta t. Okay, so that's the temporal discretization we're talking about here. So here again, no detail. There are full community of people working on knowing how you should specify those particular equations that describe the evolution from time t to time t plus delta t at the discrete level. I will not get into that, but that's all research area that we're describing here. Okay. So this is for the very basics. There are two aspects I like to just raise to your awareness when we describe those very fundamentals of ocean modeling. I guess the first idea is this idea that there are scales you resolve, and there are scales you don't resolve. Okay, that's pretty intuitive, given that we're describing things into boxes. So obviously, what happens into the boxes, we'll not know anything about it. We'll only know things about what happens at scale larger than the size of the boxes. For some reason, the transparency is kind of messy here as compared to my screen, but that's okay. Basically, we start from those primitive equations in the continuous space, and we're trying to get a set of equations that describe its evolution within a filtered space, a space where we only look at a certain kind of scales. Okay, so given some sort of averaging operator that I call R here, given the resolution, you get an equation for the evolution of your resolved scales. YR means the scales that you see at the grid scale. Will depend on the terms that you can guess from the evolution equations, but also a number of other terms there. Those terms, they come from the very fact that the evolution equation, the governing equations that tell you how your state vector evolves in time are nonlinear. Because they are nonlinear, you cannot average the you cannot, during the averaging process, you cannot forget about the correlations between what's happening at the subgrids, at the subgrid size. Okay? So basically the baseline here is that if you want to specify the evolution of the resolved state of the ocean, you need to take into account the effect of the unresolved state of the ocean, what you don't see, what you don't know. So fundamentally there's the question of how you close your problem here. Okay? So resolved and unresolved scales. So that's notion number one. Notion number two I'd like you to be aware of is this idea of the effective resolution. So far, I said we're discretizing the equation into boxes, and we know what's happening at scale larger than the box size, and we don't know what's happening at scale smaller than the box size. This is actually not strictly true. If you are looking at, so look at this plot there, if you were looking at a kinetic energy power spectra, okay, so you look at the amount of energy at a given scale in your model. Under certain circumstances, we can get a priori knowledge of this spectrum from your understanding of the very basic physics. And what we see in practical implementation with the code, with any discretized version of the primitive equations, is that there's a range of scales starting at the grid scale, but that can extend quite a bit, say up to 10 times the grid scale, where your ability to describe the evolution of the ocean is somewhat affected by the way how you have discretized your equations. Okay? So there's a range of scale there where your model is not predictive. Okay? So we define what we call the effective resolution of the model. That's the scale starting from which you can actually see and describe the evolution of the scales. Okay? So what I wanted to say here is that in a system without that assimilation that puts or feeds energy at small scales in the system, the result scales are not actually starting at the grid scale. And that's basically what I'm saying here. And this has implications in terms of what you find in CMEMS products. You need to be aware that the actual physical content of your product will depend on the result physics of the model, whether, I mean, the key ingredients that you put there, whether there are tides or no tides or things like this. That's pretty obvious. But also, there's a fundamental key difference between the effective resolution and the actual model grid step. Okay? So that's something I will come back to later. Okay, so this was for the hardcore part of it. We'll get to easier stuff now. Describing the future trends in ocean modeling with NEMO. Obviously, this is probably more of a personal perspective here, since we are, as you can guess, in a process of thinking what we're going to do over the next few years. This is actually happening right now. So that's my take on that. You might have other perspectives depending on who you're talking to. So future trends in ocean modeling with NEMO. I guess the key and obvious aspect from my perspective is that given the evolution of the computing resources and the evolution of the observing network that we can foresee over the next 10 years, it's clear that at least for Copernicus services, we will still need physically based ocean models in the future, just to meet the user's need, because we need a resolution there that is not there in the actual observation network. So we will need those models. So we'll need to improve them. And for improving them, my personal perspective is that the key drivers, there are two of them. We need to improve our physical understanding of the ocean and to translate that into bits of code in NEMO. And we also need to build that physical understanding from the confrontation to observations. I will here describe 3 trends, things that have been happening over the last 5 years that somehow are likely to imprint the evolution of CMEMS products in the future. This is just a selection. I could have picked up other examples. So trend number 1 is getting toward kilometric effective resolution. You could tell a story like this. Basically, within 5 years' time now, or 6, we'll get an information about sea surface height down to scales of 1 kilometer, or say a few kilometers, thanks to SWOT altimeter mission that will be launched in 2021. So this particular altimeter mission will provide an information on the dynamics at a scale smaller than the actual scale of the products we have right now. And from an ocean dynamics point of view, you know that at scales smaller than 50 kilometers in the ocean, there are a large range of physical processes that are fascinating to the oceanographer, and that we suspect that those scales are playing a key role in some climate functions of the ocean, for absorbing heat from the atmosphere, for allowing kinetic energy to transit from the large scale to the small scales in the ocean. So we'll observe that with SWOT, or at least we'll get some hints of it. And clearly, one key objective of NEMO over the next few years is to improve its ability to describe consistently those scales down to kilometer scales. Okay? I here just show one example of pilot study that we've undertaken in Grenoble about that. So that's one particular model simulation that we've performed. Don't want to get into the detail here. I guess the key aspect here is that we're using a very dense horizontal grid and a very dense vertical grid, and that is very expensive. Okay, that's the only thing you need to know here. The model setup is as realistic as we can afford for that kind of exercise, with realistic boundary condition and atmospheric forcing. One thing I'd like just to highlight here is this. So this is the surface or almost surface. It's at 100 meter. Relative vorticity of the ocean you get in that particular simulation that we've performed. So what is it? We're here talking about relative vorticity. Relative vorticity, you can just get it like if it's blue, it means that you're turning that way. If it's red, it means that the current is turning the other way. Okay, so it gives you an idea of how swirling the local dynamics is in the ocean. So the first thing you see here is that it's very bright red and very bright blue. So meaning that when you get to small scales, you have a lot of things that turn in the ocean. You can see also that there are very small scales there, down to very, very tiny scales here, down to a few kilometer scales. So the ocean is populated with a wide and very large range of physical processes that range from large scale to small scales. And the most impressive things we've seen with that particular simulation is that if you look at the same very similar plot 6 months later in summertime, you see a very different perspective here. Very different scales, very different level of energy there. Okay? So what you see is that there's a very strong seasonality in those scales that are not described right now in CMM's product. How we'll cope with that in the future is something we need to figure out, but definitely we'll need to face this idea that there's a very strong seasonality of the mesoscale dynamics in the ocean. Now, if you want to go that way, obviously you need to first, I guess, identify some open questions. And from my perspective, there are two of them. How robust are the model prediction in this range of 1 to 10 kilometer scales? I don't know. How do you optimize or make this compromise between cost and your ability to resolve the dynamics? How do you choose your grid, your vertical and horizontal grid? I don't know. The only thing I know is that if you want to make progress there, it's through comparison with observations. And there are only very few observation networks that can help us there, because we need long-term, dense networks that measure velocity in the ocean. That's one of them here, collected during the osmosis field campaign driven by our UK colleagues a couple of years ago. Trend number two. Trend number two is getting towards a probabilistic description of ocean dynamics. What am I talking about here? If you take a general perspective as to what we're doing here with ocean modeling, you say what we call a system approach to ocean modeling. We're basically trying to describe the evolution of a system that combines two things: things we know and things we don't know, things we observe and things we don't observe, things we represent explicitly in the model and things we don't represent explicitly in the model. Okay? So there's a fair level of uncertainty in our ability to describe the evolution of the whole system, given only a knowledge of what we know. So far in ocean modeling, we've described the evolution of this system as being only a function of this system. The point is, the uncertainty can affect the evolution of the system itself. And you need to somehow represent the propagation of the uncertainty during your integration process with your ocean model. Another perspective to look at that is this kind of plot here. If you go at sea in the ocean and measure, say, sea surface height at one point, you just build a statistical description of it over long time scales, what you'll see is that there's a fair chance that the variable you're looking at will have a multimodal distribution, meaning that one particular trajectory of the system might not be a good description of the actual system itself, because there are several possible states that are compatible with your a priori knowledge of the system. Okay? So without getting too much into the concepts here, I'd just like to let you know that there are two key building blocks that will be key for the evolution of NEMO in the future. The first is the ability to perform ensemble simulations and not only single simulations for doing forecasts but also hindcasts. The idea of using more systematic stochastic perturbations of your resolved dynamics so that you could put noise in the system and see how it evolves with your ocean dynamics. Just an example here. So that's a slide from Thierry Pendeux from an ongoing project here. What you see is the Gulf of Mexico here. The lines there are contours of sea surface height, daily sea surface height. And what we're looking at is the distribution. So that's from a model experiment with a large number of ensemble members describing the evolution of the same physical system, same forcing, same equation, same resolution. And what we see is that in certain places, if you look at sea surface height, you get a monomodal distribution, like here within the Gulf itself, or here in the Caribbean Sea, a monomodal, same kind of Gaussian kind of a distribution. But in some other places, like here, within this loop current region, you have a bimodality in the possible states of the ocean, which means that if you were only look at one single trajectory of the system, you could probably just be missing what could happen with another state. That's point one. And point two is, if you're performing an ensemble and only looking at the actual ensemble average, the state you will get from the ensemble average will fall pretty much here, which is basically the less likely state of the ocean. So we need to get into a probabilistic distribution description of the ocean. We need to describe the ocean in terms of probability distribution function and not only in terms of trajectories. Okay? Just getting quick to the conclusion on that aspect. This can be done for a large number of aspects of ocean dynamics. Here, that's an example for that sort of application for biogeochemistry. You could do the same for sea ice. Definitely, your whole perspective on your ability to model the evolution change dramatically when you get into this probabilistic description. And what changed also dramatically is your ability to confront your model and your observation. Because it's not one particular model trajectory with the observation that you confront here. It's a whole network of possible state, and you look at where your observation lie within this range of possible states. So basically, we're at the verge of a situation where we'll switch from a deterministic description of the ocean to a probabilistic description of the ocean. So that's trend number two. Trend number three is, well, one of the conclusions of all the user meeting for CMMs is that users need more resolution. The problem is resolution is expensive in terms of computing resources, so we need somehow to come out with solutions for increasing locally the actual resolution of the product. To do that, there are approaches. The one we're pushing forward with NEMO is this idea of using block-structured a mesh refinement capability. So there are from a very general standpoint, two types of meshes for geoscientific models. Either what we call structured grids or what we call unstructured grids. NEMO falls within the frame of structured grids. It has many benefits, and especially in terms of efficiency, in terms of high performance computing. Now, depending on the type of method you fall in, you would have different approaches to your local mesh refinement strategy. If you're within the frame of unstructured grids, you would simply define your grid. You don't care about the structure of it. You just put points where you need them, and you can have an increased resolution, say here as an example, along the coast of the US, because that's where you know that small things are happening. Now, within the frame of NEMO, what we're using is this ability to refine locally blocks of things. So that's an example here coming from Jérôme Chanu quite a while ago. That's in Labrador Sea. You see here the very coarse grid and here the very high resolution grid. We have the implementation for that. It's called Agrif. It's in NEMO, and it works. The point is, we want it to work better. We want it to work better, and in particular, we want it to be more flexible, to be more easy and more flexible to use within NEMO. To do that, we need to go to a situation where we can have a large number of Agrif nests. So that's an illustration that you have here from Laurent Debreu, where a pilot application here is using a very large number of Agrif nests. There are enough a number of algorithmic issues that should be solved for this. But we're slowly getting there, and that's quite an exciting trend from my perspective. Still, we need to come out with rationale for choosing, to define how you locally refine your grid. We'll need to think about how we adapt the result physics to the model, to the model resolution, and we also will need to think about how we use this sort of things within the frame of CMM's products. Getting to the conclusion, because I see Jan is nodding. I'm late. But here are the conclusions. That's just a wrap-up. I guess all this is just what I've been saying so far. The thing I'd like to raise is this very important dimension from my standpoint of the European dimension of NEMO. That's how we reach that point, and we need to keep that momentum going. You've been introduced to the very basics of ocean modeling and to some notions as to the actual resolution and what you can get from the product. And you've been introduced to some trends. this idea of going to higher resolution with a probabilistic description of the ocean and probably with a multi-resolution capability. How this will basically, and I think all this will help in the future to better match the user's need within CMMs, so better resolution and a better ability for users to use the products for performing risk analysis. There are other trends. I could have discussed many things, and I'm already too long. Thank you for your patience.